Hey y'all, Data Guy here. And today I have a video for you where I want to talk about how you can build reliable, scalable, and maintainable data-powered applications. So in my mind, any application is really just built around serving data in a certain way to end users. You have analytics dashboards, but even things like social media. Facebook is really just a not a centralized database that everyone can read and write to look at each other's social logs. Each post you can think of as an entry within a new row in a table. And so with that in mind, I want to really just talk about how you can build an effective data-powered app and really, bring all that lovely data that your organization might be using into an actual real-world use case, but do it in an effective and efficient way. Because it's really easy for someone to throw together some little proof of concept, minimum viable product that is just like, hey, look at this cool dashboard I built. But what I want to talk about is really taking that a step further and how you can turn those kind of cool little projects into scalable and maintainable systems. So I'm going to talk about first about how you should think about data systems, then go into how you can build reliable data systems, scalable data systems, and then also making sure that you can maintain those over a long period of time, even if someone leaves the organization. So let's get into it. So first, I want to go into how we would really think about data systems, and at a super simplistic level, which I have up on the screen. Data systems are really just the backbone of your application. It can encompass things like databases, caches, messaging systems, and more. But really the flow is going to be, you have some end user that is interacting with an application that is then using a interface that you've designed through that API, that application programming interface, to determine how those assets will be used to invisibly serve the desired end result to that user. And you're going to want to think about, when you're designing systems, consider data integrity, consistency, and availability. Data integrity, ensuring that your data remains accurate and consistent across the system, preventing corruption and loss. That is, core to making sure, hey, especially if you're in some kind of industry where you have regulated data, preventing that corruption of data can save you even some jail time. And then consistency refers to the guarantee that all users see the same data at the same time, which can be particularly challenging in distributed systems at a large scale when you have to serve data to hundreds or even thousands of end users. And then finally, availability ensures that a system is always accessible and operational. So when you're just even beginning to think about your data systems, make sure that you have a plan to hit all three of these paradigms. And so understanding the specific needs of your application and then the trade-offs involved in that data system design is really essential. And for instance, the CAP theorem states that it is impossible for a distributed data system to simultaneously provide consistency, availability, and partition tolerance. So you're never going to perfectly hit all of them. So you really just need to say, hey, what are the most important of those three according to my application's requirement? Maybe I'm not in a super regulated industry. Maybe data integrity, I can deal with a couple missing rows, but I need to be able to serve this data to tens of thousands or millions of users. Then you might be willing to take some of those integrity trade-offs to make it more available to a larger number of users. So now the first kind of high-level category I want to talk about is reliability, and what you can do or what issues might arise that would cause your system to not be reliable, and what you can do to prevent that. And so here I have kind of a typical data flow where this engineer has considered reliability and has multiple different systems like incident SLA management, data contracts, data quality and AI ops, data governance and lineage, many different layers to making sure that, hey, if there's any kind of fault in the system, I'm immediately notified. And the first thing that could arise are hardware faults. At the end of the day, even if you're using the cloud hardware can fail. And it can result from various causes like disk failures, power outages, network issues. There's the old story of like an AWS data center getting flooded and a whole region going down. And so to build a reliable application, it's really essential to anticipate and build plans to mitigate these faults. So some techniques could include redundancy, like RAID for storage, multiple network paths, failover mechanisms, and also the use of reliable cloud services that offer hardware abstraction and fault tolerance. The next category are software errors. Software errors are any bugs or flaws in your application code that can lead to system crashes, data corruption, or security vulnerabilities. And to minimize these errors, rigorous testing like unit testing, integration testing, system testing, code reviews, and adherence to coding standards are really crucial. So employing automated deployment and continuous integration pipelines helps you to catch those errors early and ensure that code changes do not introduce new issues. Then third, we have the good old human error. And so human errors can occur really anytime, but mainly development, deployment, and operation phases. And these errors can be mitigated through things like comprehensive documentation, really clear standardized procedures, and automation of repetitive tasks to just reduce the human in the loop risk of someone just, hey, they got their jobs clicking a button every day. One day they forget to and your whole system goes down. That's a task that can be automated. And so implementing robust monitoring and alerting systems can really help you quickly identify and rectify issues that can be caused by human mistakes. And also regular training and fostering a culture of responsibility and learning from mistakes are also important. At Google, they have a policy or Meta, they have a policy that no one is ever blamed for a mistake. You just have kind of a cold, emotionless analysis of, hey, what went wrong here? So it's really important to have that kind of culture so people feel comfortable admitting when they made a mistake so that you all can learn from it. And then the last category under reliability is, why is it so critical? So reliability is critical for user trust and satisfaction. If you have unreliable systems, that can lead to data loss, security breaches, and downtime, which results in financial losses and reputational damage. And so for mission critical applications, it's powering your business, reliability is non-negotiable. Even for less critical applications, you're going to want to maintain a baseline level of reliability to maintain, just user confidence in your application and operational efficiency, but it is kind of a sliding scale as you get away from actually revenue supporting tasks. So now that we've gone over how to build reliable systems, I also want to talk about building scalable data systems. And so here, I kind of have a guideline for how you might want to build a scalable data analytics pipeline. And the first thing, you're going to want to, there's a couple considerations really for scale. The first one is load. And load refers to the demand placed on a system, and that's typically measured in terms of requests per second, data volume, or concurrent users. And understanding the load characteristics of your application is really crucial for designing a scalable system so that you can make sure you're aligning with the actual load characteristics of the application. Then we also have describing performance. So performance involves how well a system handles a load. So that means, hey, what is the capacity of the system to actually process the data that's being, or the requests that are being inserted into it? And so key metrics here include latency, response time, throughput, which is the number of requests handled per unit of time, and then also resource utilization. So CPU, memory, disk, and network usage. Performance testing also helps identify bottlenecks and areas for optimization when you're going through this process of, hey, let's see how scalable our system is. And so some approaches for coping with load, there's a few different strategies. Number one, horizontal scaling, so just stapling on more instances of a service or a database to distribute the load. The second is vertical scaling, and that's actually increasing the size of existing instances by adding more CPU, memory, storage, whatever, just increasing the actual size of the existing applications. Then you also have caching, which is storing frequently accessed data in a cache to reduce database load and improve response times. Fourth, we also have load balancing, and that's where you distribute incoming requests evenly across multiple servers to prevent a single server from becoming a bottleneck that slows down your entire system. And then finally, you have database sharding, where you split a database into smaller, more manageable shards to distribute the load and thus improve performance as well. And those are really some of the main approaches to building a scalable data pipeline. Now, the final category I want to talk about is maintainability. And so maintainability, I kind of break down into three subcategories, which are the capacity of a system to be operable, simplicity, and evolvability. And so operability focuses on the ease with which a system can be operated and maintained. And so key practices to make a system operable include monitoring and alerting, which is implementing comprehensive monitoring to track system health and performance, coupled with alerting to notify operations teams of issues. Then you also have automation, where you have automating of routine tasks such as deployments, backups, and scaling to further reduce human intervention and error. And then finally, documentation. Providing clear, concise documentation for operational procedures, system architecture, and troubleshooting guides is key to having new people be able to quickly come up to scale and understand how a system works and how to support it. Then, under simplicity, we have, it's really all about managing complexity. So simplicity in system design reduces the cognitive load on developers and operators, making the system easier to understand, debug, and maintain. And so some principles you can follow to achieve simplicity include modularization, where you're breaking the system into smaller independent modules that can be developed, tested, and deployed separately. Clear abstractions, where you use well-defined interfaces and abstractions to hide complexity and promote reuse. And then minimalism, which is doing things like avoiding unnecessary features and over-engineering, and instead focusing on core functionality of the platform. And then our third category, finally, is evolvability, which is making change easy. No system is going to remain perfect forever, and evolvability ensures that a system can adapt to changing requirements and technologies over time. And so some practices you can use to promote evolvability include agile development, which is using agile methodologies to iteratively develop and deploy new features, allowing for rapid adaptation to feedback and changing requirements. And then couple that with continuous integration and deployment. Implement CI/CD pipelines to ensure that changes are integrated and deployed quickly and safely with the option to revert back if someone pushes a breaking change. And then finally, refactoring. Make sure you're regularly refactoring code to improve its structure, readability, and maintainability to help reduce technical debt and stay ahead of it as well. And those are really all the key kind of principles you'll need for designing a maintainable system and a scalable and reliable system as well. And so that is kind of really all I wanted to cover in this video, and really emphasize that building reliable, scalable, and maintainable applications requires a holistic approach that considers both data systems, fault tolerance, performance optimization, and operational efficiency. By understanding the principles and best practices that I've outlined here in this video, it should hopefully help you be able to more easily design and develop applications that meet the demands of modern users and businesses. So I hope you've enjoyed this video. I hope you have a great rest of your day. Data Guy out.